Good morning, everyone, and welcome to the Daily Maths Challenge, episode 4. I've got a few questions for you lined up, so let's get going. Okay, so the bronze question. These are just some simple equations to solve. So if we look at the first one, this is probably the easiest one. 3 plus x equals 20. Now, whenever you're shown an equation and you're asked to solve it, what you need to do is you need to find the missing value. So in this case, the missing value is x. What could x be? Well, we know that actually, you can just eyeball it and think, okay, well, I know that in order to get 20 after adding 3 to something, you would probably have to start with 17. So, yeah, let's just check this. This seems to work. Yep. Okay, so we found it. Well, that's good, but instead of eyeballing it, let's have an actual strategy for, working it out in general, so that if we have something harder, we have a strategy to do it rather than just trying to guess what it is. So this is what we do. We take away we take away 3 from both sides. And so if we take away 3 from this side of the equation, you're left with just x, because x plus 3, take away 3 is just x. And then you have on this side 20 take away 3, which is obviously 17. Okay, so that's one way to solve it. Just each time you change the equation on both sides, you're going to try and get closer to x. In this case, it just took us 1 step. Later on, we're going to do an equation that takes us actually 2 steps to do. Anyway, question B. 7x equals 28. So this is the equation we're starting off with. Now, as I said to you, we can do something to both sides of the equation, okay, and we'll get a new equation. And the idea is that we're going to change it to get to x equals something. Now, what could we do to both sides of this equation? Well, we want to divide by 7 because we have 7 times x here, and we know that if we divide by 7, we're going to be undoing that multiplied by 7. So we're dividing this side by 7, we should get x, and 28 divided by 7 is going to be 4, and you can just go back and check that. 7 times 4 is 28, this works. Okay, question C. Now this is the one that will take us 2 steps to do. So we start off with this one. 2x plus 10 is equal to 40. Now, what you could do, now this is what I would do. I would imagine 2x as its own entity. So something plus 10 equals 40. And then let's try and work out, first of all, what this something is. So if we start off with something and add 10 equals 40, if you want to get to just work out what that something is, what 2x is, you can take away 10 from both sides, and that way we'll get 2x equals 30. Now we've got this far, what you can do is just divide both sides by 2. Again, dividing is the opposite of multiplication, so that will get rid of the 2 at the front of the x. So 2x divided by 2 is going to be x, and then on this side it's going to be 15, because 30 divided by 2 is 15. Now, I should have mentioned this earlier. Whenever you have a number next to a letter, so 2x in this case, we mean that they're multiplying together, okay? So that means 2 times x. Anyway, so we got that now. And finally, the last question, and I put this in bold just because I felt it was a bit more challenging for you guys. Mostly because actually this is a notation that often people either forget or didn't know in the first place. So what does x squared mean? Well, if you have a number, so let me just do a new thing here. So if we have like 2 squared, that means 2 times 2. If you have 3 squared, that means 3 times 3. If you have 10 squared, that means 10 times 10. So the pattern is, the little number at the top, which is called a power or an index, is letting us know how many of these numbers, how many of these, they're called the base number, how many of these you have multiplying together, okay? So in this case, x squared, what it means is x times x is equal to 4, and we need to work out what x is. Now, in order to do this, you can think, okay, well, I know that 2 times 2 is 4, and so we're done. Well, that's half right, because yes, 2 works. So x could have been 2, but actually there's another number that it could have been as well. I don't know if you remember from last time, a minus times a minus is positive. So actually, it could have been 2 or minus 2, and those are the only options you have. Another way we could have done this is by taking the square root. So x squared equals the square root of 4. We could have square rooted both sides. Well, square rooting is the opposite of squaring, the opposite of raising something to the power of 2. So the opposite of x squared is going to be, the opposite of squaring that is going to be, we're just going to get one of those x's. And you can do square root of 4 in a calculator. So the way you do this is there's a square root sign here. You put in 4. The square root of 4 is 2. Now this will give you only the positive version. That's just a convention. But you just need to remember after getting this value, we have minus 2 as well. Now, the way that we can combine this into one line is by writing x is plus or minus 2. Now, this symbol, as I just said, is plus or minus 2. It's basically saying that there are two numbers here, either 2 or minus 2. You take the plus or the minus. And that's a useful notation to know for future. Okay, so the silver one. We're looking at regular polygons. So basically, regular polygons are just polygons where, so that's shapes that have straight sides, where every side has the same length. So let's look at a few examples. So what isn't a polygon? So, well, first of all, this is a polygon, right? But it's not a regular polygon because these sides are not the same. Now, what about this shape? This is a circle. Now, this isn't a polygon because it doesn't have straight sides. We can have other shapes like this. Okay, that's called an arrow. That is a polygon. It has straight sides. Okay, so how do we work out which regular polygons can completely tile a flat surface? By tiling, as I said before, it's basically when you can put the same shape and attach it to itself in a way, and you basically get a surface that is completely covered with these shapes, and there's no overlap and no gap. So if there was an overlap, let's say with a pentagon, you can't do this with pentagons. So if you were to go and try and overlap these guys, what you would get is something like this, where you would have to, sorry about this, it's a bit messy. So if you were to try and tile this bit up, you would have to probably overlap another pentagon, and that would be, you see them overlapping here, that would be a bit messy. So, and gaps, obviously you know what gaps are, so we can think of the pentagon example as well. You can start tiling, and if you're insisting on not overlapping them, you'll run into the issue of, okay, well, I'm not able to then tile this bit. If I try and tile this bit, it's going to be slightly bigger and there's going to be overlap. So that would be a gap here, okay? Anyway, so which polygons, regular polygons, can we use to completely tile a surface? This is useful if you want to tile your bathroom in one of these shapes and stuff like that. So this is what we do. I'm going to list, first of all, the ones that actually work. And just jump straight to the answer. So obviously we had squares already. That's the four-sided shape. Now actually we can get a three-sided shape that works as well. So a three-sided shape, obviously a regular one is an equilateral triangle. So we can tile it like so. Okay. And yeah, so imagine we can continue going on, like drawing these strips. Each strip has these equilateral triangles. You can keep going indefinitely and layer the whole thing with triangles, okay? So triangles can be done like that. Now let's look at five-sided shapes. Pentagons, as we talked about earlier, cannot be used to tile completely a flat surface. So are there any more that we can do it? Well, it turns out that we can use one more shape to tile the surface, and those are hexagons, okay? So hexagons are six-sided shapes, and regular hexagons are basically those shapes that have equal sides. So these can tile a flat surface without leaving any overlaps. And actually, you know this from if you've ever seen a beehive or beeswax or whatever. This is how honeybees kind of like form their wax. Like they have these hexagons, and actually it's interesting because the reason why they choose hexagons is because I think it's something to do with them being the strongest polygon where they can do that, and it's very efficient in terms of how much wax you need compared to how much volume you get. So for the amount of honey they want to store, they need to use minimal wax to build the sort of the outer casing of these cells. So it means they're more efficient. They don't need to use as much wax. So it's just really interesting the way that nature works. Okay, so these are your three versions. So we can have a 3-sided shape, 4-sided shape, or 6-sided shape. But we want to know why those shapes are the only shapes that can kind of do this. And the really, I think the best explanation that I can give at the moment, which is kind of quite short, is that if you look at kind of like where these shapes meet. So if you look at where these shapes meet, can you see that you have to have like a whole number of shapes around it? Okay, so let's look at these angles. So can you see that we've split a whole turn? A whole turn is 360 degrees, okay? And we've split a whole turn here into 3 parts. So 360 divided by 3, what angle does that form? That forms 120 degrees, right? So each of these angles is 120 degrees here. Likewise with a square, so it divides at a point, you have 4 squares around that point. So we're dividing that full turn into 4 parts. That's going to be 90 degrees, okay? And likewise with triangles, we have 1, 2, 3, 4, 5, 6. So 360 divided by 6, that's going to give you 60 degrees, okay? So that's fine, but how do we know that there are other shapes that can't also fit snugly around that? Triangles have 3 sides. You can't get fewer sides than that. Otherwise, that will be, 2-sided shape or a 1-sided shape, and that's not a polygon. Okay, it doesn't go back on itself. That would be like a line or something like that. Okay, so yeah, are there any other shapes that are kind of have more sides than 6 sides that fit around a point like that as well, that can also tile a shape? Now, what we can use is the fact that when you have a shape, let's say that it has n sides. So okay, I'm just going to draw a random shape, but pretend that has n sides. Okay, where n is a whole number, right? That's how many sides it has. The interior angle, which is the angle we've been looking at so far, like the angle that is in the interior of the shape. So 90 degrees in this case, 120 degrees in this case, 60 degrees in this case. There's a formula for the interior angle of a shape, and that is this, okay? If you want to find the interior angle, you do 180 take away 360 over an n. Another way of doing this that you might have seen is 180 n take away 2 and then divided by n. So these are two formula like that give you the interior angle of a shape. Now if you think about it, these the angle has to divide a whole number of times 360, because as we said earlier, we can kind of like divide 360 into 3 parts, 4 parts, 6 parts. That corresponds to the hexagons, squares and triangles, right? A whole number of them have to fit around that 360 degrees. So the interior angle, like 120 or 90, whatever, it has to go into 360 a whole number of times. And so let's look at this. So if you look at 180 take away 360 over n, let's say we're looking at ns1, ns2, ns3, ns4, ns5, ns6, ns7, and we keep going. So let's look at the interior angle for each of these, okay? Okay, so obviously we actually can ignore ns1 and ns2, right? Now ns3, we already said that's 60 degrees. That's the angle of the interior angle of a regular 3-sided shape. Similarly for 4-sided shape, we've done that. For a 5-sided shape, let's see what that would be. So, and this is going to give you an explanation as to why pentagons don't tile the surface. So we do 180 take away and then 360 divided by how much was it again? 5 sides, right? That's going to give us 108. That's the interior angle of a pentagon. Now let's see how many 108s fit round a you know, a point. That would be 3.3, and we saw that earlier, right? Can you see? We kind of we could overlap 3 pentagons, but we couldn't really overlap that next pentagon, the 4th one. There wasn't quite enough room. So anyway, so that's why pentagons don't work. And then obviously if we do this for 6-sided shape, you get 120 degrees. Now for 7, let's do this. 180 take away 360. Oh gosh, can't type properly. Divided by 7, which is going to be 128 let's say 0.6 roughly. Right, and that definitely doesn't go into 360 an equal number of times. See, 2.8 times. Yeah, you can't fit one of those in. Now, we can do this forever, but we don't have time to do that. So how can we quickly see that no numbers higher than 7 work? Well, this is the idea. If we go back to this formula, we have 180 take away 360 over n. Now, basically, if you think about it, this is always going to be less than 180, isn't it? Right, we're doing 180 take away something positive, so it's always going to be a little bit less than 180. And actually, as n increases, this term gets smaller and smaller and smaller. Okay, now this is the idea. The interior angle is never going to be as big as 180, so it can never be half of 360, which means we can never get a shape that when you tile it, kind of tiles in 2 different shapes. Okay, we've seen a hexagon can tile at 3 different points, right? So we've seen that. And we've seen that a square can tile at 4 different points. And we've seen that a triangle can tile at 6 different points, okay? So as we go from a 3-sided shape to a 4-sided shape to a 6-sided shape and so on, this formula for the interior angle is getting bigger and bigger. But so you're going to be able to fit fewer nut shapes around the point as you go. Now we've got to 3 with hexagons. There's only space. There are only, like, if the angle increases, the only other number of sort of equal angles that can fit around a point is going to be 2, right? It's going to be 2, which is in the case of, well, the interior angle is 180. But as we said earlier, you can't get the interior angle being 180 because it's always going to be slightly less than 180. So that's basically why there are no other shapes that can tile like that, in that way, where the shapes meet at points, at vertices. It's because they're simply, you know, all those shapes have been taken. Like, you know, we can't fit any more than, any less than 3 around a point. Okay, let's go to gold. Now for this one, I'm actually not going to start at, I'm not going to go through straight away all of them. I'm basically going to give you the answers to A, B, C, D, and E, but I'm going to wait until we get to D to actually show my process for doing it. But I'm going to kind of tease you a bit because I'm going to show you a shortcut. Now, a lot of you might have kind of like, when it comes to A, just have gone on adding on your calculator, right? So actually, we're looking at powers of 3. So 3 to the power 1, 3 to the power of 2, 3 to the power of 3, and 3 to the power of 4, and so on. So, you know, we could have, you know, you could have typed it on your calculator. So what is 3 to the power of 5? We're going up to 243. Okay, now, yeah, that's 3 to the power of 5. So, yeah, you could do it manually like that, but actually that's going to take more time. And especially if you have a question where you go higher than this, you need to come up with a different strategy. Otherwise, that's going to take a lot of your time. And I'm going to show you a bit of a sneaky method of doing it. And I'm going to show you actually how I got it. So you might have got this. So let me just write down my one. So I'm going to do 3 to the power of 6. Take away 1 over 3 take away 1. So you should get What's 3 to the power of 6? Let me just do that on my calculator. 729. Take away 1 over 2, which is going to give me 364. Okay. So, yeah, so that's that one. And so you might wonder how that works. We'll get onto that. But for now, let's go on to B. Okay, so we have 1 take away 2 plus 4 take away 8 plus 16 minus 32 plus all the way to 256. Now the pattern is I am I'm adding the powers of minus 2. Okay, so again with minus numbers, if you times a minus number by a minus number, you get a positive number. If you times a positive number by a minus number, you get a minus number. So this is going to alternate positive, negative in that fashion. Okay. Okay, and then minus 2 to the power of 8 is where we stop. Now, I'm going to use my sneaky formula. So I'm going to do minus 2 to the power of 9. And you might have worked out by now what's going on. So I'm going to add those together. So that's going to give me minus 2 to the power of 9. Take away 1 over minus 2 minus 1. That's going to be 171. So that's the answer to that one. So well done if you got that. And now for the next one, this is when my formula really comes in handy, because this one definitely I do not have time to manually type it into my calculator. Okay, so for this one, I'm going to say, okay, well, I'm going to do 4 to the power of 101 over 4 take away 1. And let me just type in my calculator. So that's 4 to the power of 101 take away 1 over 3, because 4 take away 1 is 3. Wow, that's a big number. So that's basically standard form it's been written in. If you don't know that, what that means, it just means that we're expressing that number as a number between 1 and 10 times by power of 10. It's just how engineers and scientists love to express big or small numbers sometimes. Okay, so basically it's basically got 61 digits in it, which is pretty big. Okay, so now we got to question D and E, and this is when I'm going to show you the trick that I've been using. So for question D, I'm going to show you how I got it. For question D, we have this thing. So we're going all the way up to x to the power of n. N could have been any whole number. So if n is 3, we're doing 1 plus x squared plus x to the power of 3. If n was 100, we'd be doing like what we did earlier with the powers of 4. We're going up to 100. So this is what I'm going to do. I'm going to say that this is a. Okay. So now I'm going to look at, okay, what is a times x? What is a times x? Well, if I times a by x, I'm timesing this by x, because this is a, right? Another way of saying ax is just this times x. And if I times this by x, I'm going to get x plus x squared plus x to the power of 3, right? I'm timesing by another x for each of those ones, right? All the way up to x to the power of n plus 1. So, okay, so I have those two. Now what I'm going to do, I'm going to do ax take away a. Now, think about it. I'm going to do this, take away this one, but for each of these ones, apart from the end one here, if I take away a, I can cancel these with, you know, the corresponding one with the this line. Okay, so I'm ending up with x to the power of n plus 1. Take away this. This is the only surviving expression from a that doesn't get cancelled, minus 1. So, but what I have here is ax minus a. I can factorize an a, and that's going to give me this. And then I'm just going to divide by x minus 1. Okay, and then I have an expression for a, and that's what I've been using. Can you see all along I've been doing, okay, whatever power I'm going up to, I'm going to do the power, the power that's just 1 greater than the biggest power here. So in this case, the power is 101. That's 1 bigger than 100. And then I'm going to take away 1, and then I'm going to divide it by the base x, take away 1. Okay. So that was the trick. Now, how can I use this trick to show you? Well, how can we work out what if we have a number that is less than 1, if we do this forever, okay, if we keep going, what does that number tend to? What is it basically, if you do this infinitely many times, what is it going to be? So it's really important that we have a number that is less than 1, because if it wasn't, let's say just 2, can you see that each time this is getting bigger and bigger, and actually if you add up infinitely many of those numbers don't get smaller eventually, they just exploding, they're getting bigger and bigger exponentially. So really that's gonna, if we add all them up, you're gonna get infinity. So that's why we had to say that x is less than 1, because if x is less than 1, let's say a half, so 1 plus a half plus a quarter plus we're gonna then add an eighth, and then, sorry, I don't know why I've done that, plus, and then we keep going, we're getting smaller and smaller each time, we're adding a smaller number, but it's small enough each time that actually when we add all of them together, it will be a number which is not infinity, right? It's actually a decent, reasonable number. Okay, so how can we use our formula for this? Well, this is the idea. Let's say that we know that if we just add all the way up to x to the power of n, that is x to the power of n plus 1 take away 1 over x minus 1. Now, imagine if we're adding the next one along, then the next one along. We're increasing n each time, right? This sum is going to get bigger because n is getting bigger. And so this power is the only thing that is changing in this expression here for the sum. And so you have a power that is increasing, but remember this number x is less than 1. So this is actually going to get smaller and smaller and smaller until when n becomes infinitely large, roughly, we say that actually this is going to become 0. So we get, in the end, we're going to get minus 1, because minus 1 is the only thing left on the top, and then x minus 1. But actually that can be expressed by timesing both sides by minus 1 as 1 over 1 take away x, okay? So let's say that we have, what if x is a half, like I said? So if x is a half, this is going to become 1 over 1 minus a half, which is going to be 1 divided by a half, which is going to be 2, because 2 halves go into 1. And actually there's a nice way of visualizing this. So let's say that this is 1. This is 1. I'm then going to add a half, and then I'm going to add half of that, which is a quarter, and then I'm going to add half of that, which is an eighth. And then if I keep going, can you see I'm actually going to approach this line here eventually if I do this infinitely often. And how big is that? Well, that is 1 plus 1, that's 2. Okay, so that's just a visual idea of what's going on. Each time you add the next power of a half along, you're actually going halfway in between where you have left to go to get to 2, right? So halfway along from this bit to 2 is 1. Then I go halfway along again, adding a half. Then I'm adding half again, which is a quarter. And I'm going half of the way in between. Now obviously we can get as close as possible to this line as we want. We're never going to cross it, but we are going to get as close as possible. That's why it kind of goes towards a 2. And actually at the limit, when, you know, as we go to infinity, we will actually get to 2 finally, but you need to do it infinitely many times. Alright, thank you for that, guys. Thank you for tuning in. Yeah, it's been, that is a really good fact to know, actually, the goals one in particular. This formula for finding the you know, the sum from 1 to 1 plus x squared plus x to the power of n. That's a really important formula. I've used it so many times, especially when I went to university, but also when I was at A-level and GCSE as well. So yeah, it's a really useful thing. So yeah, thank you. Again, if you want me to go through anything in particular, just let me know. And but at any rate, I look forward to seeing you on the next challenge. Okay, thank you. Bye.